Hello friends, now we will start with the next filter, that is all pass filter, or next active filter rather, that is all pass filter. In all pass filter, when we talk about all pass filter, what is the purpose? It allows all the frequencies to pass through it. So if it is allowing all the frequencies to pass through it, then where is the question of filtering? Basically, all pass filter does not perform the function of filtering, rather it performs the function of phase shifting in the signal. We will see that how it shifts the phase. So for analysis of this particular circuit, what do we do? Say this is node A, this is node B. So for analysis of any operational amplifier circuit, what do? We find the voltage at non-inverting terminal first and then apply KCL at this node A. So voltage at node B. What is voltage at node B? So voltage here is V in. So voltage at node B is nothing but voltage across this capacitor. I will be taking S domain first to find the transfer function of this filter. So this impedance divided by sum of 2 multiplied by input is voltage at node B. So voltage at node B is 1 by SC divided by R plus 1 by SC multiplied by input voltage. That's it. And we know for ideal op-amp, what is there? For ideal op-amp, the voltage at inverting terminal is same as voltage at non-inverting terminal. So voltage at inverting terminal is VA, voltage at non-inverting terminal is VB, and that is nothing but 1 by SC divided by R plus 1 by SC into V in S, or that is equal to 1 by 1 plus SCR into V in S. I hope that is clear, right? Now, applying KCL at node A. When you apply KCL at node A, we get VA minus V in S divided by resistance R1 plus VA minus V naught S divided by resistance R1, and that is equal to 0. Remember, current in this circuit is VA minus V in by R1. Current in this circuit, this side is VA minus V naught by R1. And current entering into inverting and non-inverting terminal is 0. That is biasing current of op-amp is 0 for ideal op-amp, right? So that's why we have not considered this component of current here. So VA we have already seen. So VA is nothing but VB here. I can write for ideal op-amp VA is same as VB. So I can write VB here. That is same thing. And you can write V naught can be written like this. R1 is there, R1 is here. So that can be written like this. Twice VB minus V in, right? And you know what is, this is V naught. You can write it as a function of S. And you know what is VB? VB is this. So that is 1 by 1 plus SCR minus 1 into V in. V in I have taken common, right? So that gives V naught S equal to, now that is nothing but 1 minus SCR divided by 1 plus SCR into V in S, right? So this is the output voltage of this circuit. I can further write it like this, that is, the transfer function of this filter is nothing but V naught S upon V in S, and that is nothing but 1 minus SCR by 1 plus SCR. If you draw the pole zero diagram for this circuit, this is S plane, this is S plane, this is sigma, this is j omega. So how many zeros it has? Put numerator polynomial, this polynomial equal to 0, that gives me 0. Put denominator polynomial equal to 0, that gives me pole. So what will be the factor of this? That is S equal to 1 by SCR. What will be factor of this? That is S equal to minus 1 by CR, right? So that means this gives me 0, which is located on real axis. So this gives me S equal to 1 by CR, and this gives S equal to minus 1 by CR. So I have, that is a pole located on left hand side and 0 located on right hand side, but both are symmetrically located about j omega axis. So all pass filter has all the poles symmetrically located about j omega axis on left hand side and right hand side. All zeros are, I repeat, all zeros are located in right hand side, all poles are located in left hand side. So poles and zeros are symmetrically located with all the zeros on the right hand side of S plane and all the poles on left hand side of S plane. So this is pole zero diagram of all pass filter. Now for frequency domain, what do? We replace S by j omega. So by replacing S by j omega, I can write the transfer function for this filter, right? So the transfer function for this filter will be, or rather than saying transfer function, we can say gain of this filter can be written in terms of frequency. That is transfer function when it is S, and when you take when you replace S by j omega, you can call that either gain of the filter or transfer function in frequency domain, right? So here let us see. So for frequency domain, I will be replacing S by j omega here. So for frequency domain, we will replace S by j omega. So let us see what will happen to the transfer function. So for frequency domain, what is S? S is equal to j omega. So the transfer function becomes H j omega equal to 1 minus j omega CR divided by, that is divided by 1 plus j omega CR. That is what you have, right? Now you can find magnitude of this. The magnitude of this will be 1 plus omega square C square R square under root, and this magnitude of this will be 1 plus omega square C square R square under root. So it means the transfer function has magnitude of unit. It means the magnitude of the gain remains constant and independent of frequency. That is why we say it allows to pass all the frequencies through it, and all the frequencies here will be reaching at the output. So it is not attenuating any frequency, right? So now let us see what will happen to the phase. The phase angle of the transfer function of this is minus. So I'll say this is minus tangent inverse omega CR. That is phase angle for the numerator, and phase angle for the denominator, so it is minus sign minus tangent inverse omega CR. So this gives minus twice tangent inverse omega CR, right? That is the phase angle of this. So now if you see, the frequency is normally varied from here to here, 0 to infinity. So when frequency is 0, at omega is equal to 0, if you see the variation at omega, or when frequency is varied from 0 to infinity, what will be happening to the magnitude of this and phase angle of this, right? So magnitude at omega is equal to 0 is 1, and magnitude at omega is equal to infinity is 1. Phase angle here, magnitude is independent of frequency, so that is why it is 1. But phase angle at omega is equal to 0 is what? Phase at omega is equal to 0 is 0. Phase angle at omega 0 equal to 0 is 0. And at omega to infinity, when you put this equal to infinity, so this phase becomes 90 multiplied by 2, so that becomes minus 180 degree, right? So the maximum phase angle or phase shift provided by the all pass filter is minus 180 degree. So that is how this circuit provides the phase shifting. So by varying frequency of the input signal, I get the different phases at the output in comparison to the input. So that is why we call this circuit as phase shifter circuit. So that means shifting the phase. It is not changing the magnitude of the it is not changing the amplitude of the input signal, right? So that finishes your filters, that is nothing but all pass filter. So now we will see the different questions which appeared on all pass filters. So wait for my next part.
Now let us see the example based on the all pass filter. So the question here is, for the circuit of the figure with ideal operation amplifier, the maximum phase shift of the V out with reference to input is. You have to find the maximum phase shift for this circuit, and we have just seen this is the circuit of what? This is the circuit diagram of all pass filter. The phase shift for this filter is given by, that is equal to minus 2 tangent inverse omega RC. That is what you have. Fine. At omega is equal to infinity, the frequency can vary from 0 to infinity. So what is the maximum possible frequency? Infinity. So at omega is equal to infinity, this will be minus 2 tangent inverse infinity, and at tangent inverse infinity, what is the value of this? This is equal to 90 degree. So this gives minus 180 degree. So maximum possible phase shift is, by this is plus minus 180. Reason plus minus 180 means it is including the whole range of omega, maybe from minus infinity to plus infinity. Otherwise this is your answer which is given here. So that finishes your all pass filter. So in next video we will see the generalized expressions of all pass filters.